Hello, and welcome to another edition of the Kiwi Astronomers. Our man, John Drummond, couldn't be with us this weekend, but we are very happy to have with us Alan Gilmore, who was previously the superintendent at Mount John Observatory, part of Canterbury University. And Alan and his wife, Pam Kilmartin, have what's the word I should use about being on the stamp, Alan? The honor of being on a New Zealand stamp. And another person on the stamp was Beatrice Tinsley, who is a very famous astronomer. Anyway, that's Alan, and he's here today to talk to us about asteroids. Welcome, Alan.
Thank you.
All the way from Tekapo.
That's right. Yes.
Is it sunny Tekapo or overcast Tekapo?
It's overcast in Tekapo, so we didn't see the eclipse because of the overcast, and it's still overcast, and it's going to rain later today.
Oh, that's very sad. It's wonderful here in Auckland. Wonderful sunny Auckland. We had a wonderful view of the blood moon, and we were very happy. We can't go out, but we were very happy looking out. So anyway, we're going to talk about asteroids, and John Drummond has previously talked about comets, so Alan's going to focus on asteroids. And so the first thing I'd like to know, Alan, if you could simply tell us what's actually the difference between an asteroid and a comet.
An asteroid is a lump of something solid, sort of rocky stuff that isn't fizzing off material that we can see, whereas a comet is also a small solid body, anything from hundreds of meters to kilometers across, that has ices in it that are evaporating because of warmth from the sun, and so it's producing a cloud of dust and gas around the comet. But in recent years, the distinction has become a bit uncertain, because we find that some of the asteroids in the outer part of the asteroid belt occasionally fizz off material. So the distinction is a little bit vague now as we gather more information. But basically, an asteroid is an object that is not obviously fizzing off material, gases and dust.
And how did asteroids come to be formed?
We think the solar system, the planets, formed originally in a big cloud of dust and gas, and stars first of all formed in that. And leftover material made disks around stars, and then those disks of dust and gas gradually condensed, gathered together to make asteroid-sized bodies, and then those gradually gathered together again and made planets. But the leftover stuff was basically asteroids. So they are more or less the original material that the solar system formed from.
And where do they live, these asteroids?
The ones that now survive live in two zones. There's one zone between Mars and Jupiter. We call that the main belt asteroids. And there's a second zone that's around and outside the orbit of Neptune. We call those the trans-Neptunian asteroids.
Oh, well, we can sort of not worry about them right now. Let's talk about the main belt ones. So that's all okay. I mean, I think when you mention asteroids, people are always thinking about impact on Earth. That and maybe mining these days in the money-minded society of today, but they're always thinking about impact on Earth. So they're all happily going around outside, beyond Mars, but then something happens, right?
Yeah, what happens is asteroids bump together occasionally and break chips off each other, and those chips are anything from just pebble size right up to kilometer size. And what happens is there are zones in the asteroid belt that if an asteroid is orbiting, say, 3 times around the sun to 1 time of Jupiter's orbit, then it builds up what's called a resonance Jupiter is sort of regularly pulling on that orbit as the asteroid passes by. And so the orbit starts to become elongated and ends up coming across the orbit of Mars and into the inner solar system. Well, when asteroids collide and make chips, those chips, first of all, they're not in those sort of zones, but the action of sunlight on an asteroid, on a small body, it warms it up and the object is spinning, and some of the heat that is then radiated away from the asteroid has a tiny propelling effect. It's called the Yarkovsky effect. It was first calculated by a Polish engineer back at the beginning of the 20th century. And the Yarkovsky effect has a very slight propelling effect that gradually shifts the small asteroid into one of these, what we call resonance zones. That is 1/3 of Jupiter's orbital period, or some fraction of Jupiter's orbital period.
So,
and then after that,
can I stop you there just so I'm clear? So they're going round and round in the main belt, and then Yarkovsky effect and the effect of Jupiter somehow throws them out of their nice happy orbit.
That's right. Yes, the Yarkovsky effect moves them into one of these resonance zones, like 1/3 of Jupiter's orbital period. And then after that, it's gravity of Jupiter regularly working on it that changes the orbit into an elongated orbit that comes inside the orbit of Mars.
So instead of going round and round, it suddenly starts going a bit wonky into a kind of elliptic, and then that's when the issues for places like Earth start, right?
Exactly.
All right. That's like, I suppose, going on an orbital motorway and all of a sudden taking an off ramp, and then the next thing you know, where am I? And then you're driving all over the place trying to get back, and you're never getting back. Is it something like that?
Yes, exactly. Because what happens once it starts to cross the orbit of Mars, it becomes what we call a chaotic orbit. You can't predict it in the long run, because a tiny error in predicting where it'll pass a planet becomes a much bigger uncertainty after it's passed the planet.
I see. I read somewhere that these orbits have got some funny names, all beginning with A for some reason. Is that right?
Well, they're named after the various categories of orbits are named after usually the first asteroid that was discovered in that orbit. So you've got 4 main types. There's the Amor objects that cross the orbit of Mars but don't cross Earth's orbit. They're named after the asteroid Amor, which was discovered back in the early 20th century. Then there's the Apollo asteroids that cross Earth's orbit, but in general, their average distance is greater than Earth's orbit, so they take more than a year to go around the sun. Then there's the Artems, which weren't discovered until about the 1970s, and they have orbits that are smaller than Earth's orbit, so they go around the sun in less than a year, and they cross Earth's orbit. And then quite recently, a whole category has been discovered called Asteroids. Their orbit is smaller than Earth's orbit. They are always inside Earth's orbit, and they don't cross it. So you've got these 4 orbit types.
Are all asteroids start with the letter A?
Sorry, are all asteroids?
All asteroids start with names of asteroids start with the letter A, because they're 4 then, they're all starting with the letter A.
Amor, Apollo.
Amor, Mars, they could all have Latin names.
They do all start with A, that's right.
I didn't go to school just to eat my lunch. I was wondering if it was like boats, because in classes often, K class, all the boats start with the name with a K, except for mine. But that's all right. So those, which are the dangerous ones for Earth?
The ones that cross Earth's orbit. So the Apollos and the Artems both cross Earth's orbit. Right. And so they're the dangerous ones. The most dangerous asteroid currently is an Artem that was discovered back in 2004, and it goes around the sun in 10.5 months, and it crosses so it's crossing Earth's orbit every 10.5 months. But in 2029, it will make a very close approach to the Earth, coming about 30,000 kilometers from the Earth. And it's about 300 meters across, so it's a very significant object. They want to keep an eye on it.
300 meters across.
Mm.
What would happen if that landed in the ocean?
Well, anywhere it came down, it would be a problem because the impact energy is measured in about the strength of several magnitude 9 earthquakes. I can't actually remember what the figure is, but it would have a very high impact energy.
300 meters across. What about that one that went into Chicxulub? Is that right?
That one we think was about 10 kilometers across.
Oh, so not so bad then.
Right.
Oh, that'll be all right.
We get hit on average. We get crater studies on the Earth, so we get hit about 3 times per million years by a 1 kilometer sized asteroid.
And is it possible for an asteroid like that to knock us off course?
No, they're very, very tiny compared to the mass of the Earth, so they don't have any effect like that.
So do we have any sort of, we've got some plans, right? Somewhere I read about pushing and pulling and asteroids. What's that all about?
Well, there's various ideas on if we discover an asteroid like the one that's going to pass by in 2029, if we found that something like that was going to hit us, and we had decades to do something about it, then what we need to do is just tweak the orbit very, very slightly so that it's crossing Earth's orbit a little bit ahead or a little bit behind the Earth at this dangerous time. And the Earth only takes about 6.5 minutes to cross its own diameter, to move its own diameter in its orbit. So you need only have the asteroid arrive a little bit early or a little bit late, and it will miss the Earth. So there are several ideas. One is called a gravity tractor, where you simply park a spacecraft near the asteroid, and the gravity of the asteroid is pulling on the spacecraft, but equally the spacecraft is pulling on the asteroid. And you have the gravity tractor has its own little solar-powered rocket ion engine, and that just keeps it at the right distance from the asteroid. And it just gradually, over a very long time, just shifts the orbit very slightly. Another way is to have a big mirror that you unfold in space, and you focus the sunlight on the asteroid. So stuff fizzes off where the hot spot on the asteroid, and that stuff fizzing off has a slight rocket effect that pushes the asteroid very slightly.
Is that like our own Yarkovsky effect?
Well, it's a kind of, no, the Yarkovsky effect just uses radiation. Whereas this is using material that's coming off the asteroid.
Okay. But it would be like the James Webb, right? In reverse. So you'd want it to see the sun.
Yeah, exactly.
And it would focus all the light onto it. So we have the technology, right? We just got to turn it around.
That's right. Yeah. The other one is to hit the asteroid with something. If it's not a very big asteroid, hit it with something heavy, and you change its orbital period slightly, the time it takes to go around the sun. That's doing it.
Yeah, and actually, aren't we going to send something up soon to try that out?
Yes, there's an experiment called the DART experiment, and what the target is not exactly a big asteroid, but
just as well. Start small, right?
That's right. The asteroid has a little moon going around it, and what they're going to do is they know how long the moon, the small moon takes to go around its asteroid, and they're going to hit the small moon with a spacecraft, and then see what change they make in the time it takes the small moon to go around the asteroid. They expect it will cause a change of maybe something like a minute in the orbital period of the moon, but they can then measure that afterwards.
And how big is this moon?
Oh, I think it's only, I can't remember exactly. I think it's only 100 or a couple of 100 meters across.
Oh, but we know, obviously we can see things like that, yeah?
Yes, we can detect, we can pick up that one, yep.
All right, and obviously if things go wrong, it's not going to have any impact on Earth.
Oh, no, it's the asteroid is not dangerous to the Earth.
Okay, so where do you know how is it? Obviously, it's a long way away. Is it an Artemis or an Apollo or an Amor or what is it? You know. That was a clever question by me. Ha ha ha.
I think it is probably an Apollo, but I'm afraid I don't have that information nearby.
You'll have to Google it when you get home. Oh, you are home. When we finish. So anyway, so I mean, I don't know how many people out there have seen that Bruce Willis film where they landed on it. But whenever I talk about this, it always comes to my mind that him and Ben Affleck. But I've heard quite a bit about mining, asteroid mining. What's that all about?
Yeah, I'm not entirely sure of what they're aiming for. There are some minerals, some chemical elements that are more common we find in meteorites than they are on Earth, and there are ideas that we might mine asteroids for those. There is one asteroid we think in the main belt, long way away, which we think is pretty well pure iron or nickel iron. That would have been the core of an asteroid, a big asteroid a long time ago, but all the rocks that were covering it have all been knocked off by impacts. But another possibility is to make fuel, rocket fuel, by extracting water and maybe other volatile chemicals from certain kinds of asteroids. So we don't have to carry if we want to explore the solar system, we don't have to carry all the rocket fuel out from Earth into space. We could, if we could find a suitable asteroid, capture a suitable asteroid, we could extract the stuff from it, the liquid stuff, and make rocket fuel from that.
But Alan, we haven't really gone very far, Apollo 11 and the Apollo missions, and then we stuffed around for a long time, and now we've got 3D printing, and we're putting billionaires, 100 kilometers up there. How the heck are we going to go to an asteroid, extract the metal, build something out of it? That would be like hundreds of years' time, wouldn't it? I should have thought. Given the progress, given our space progress.
Yeah, there are all kinds of ifs in it. I mean, any humans going outside the Earth's magnetic field are first of all at risk of cosmic rays. So even just traveling to the moon is a pretty risky business. They were lucky that they got away with it during the Apollo program back in the late 60s and 70s. Yeah. But they were keeping a very close eye on the sun because they were very worried about solar flares. If the solar flare had occurred while the astronauts were outside the Earth's magnetic field, which is most of the time they're flying, that could have been very dangerous for them.
Yeah, and I think Mars missions, they've got to have some kind of shielding, haven't they?
Yeah, and I don't think there's any technology that's currently in sight that can protect from solar rays, from cosmic rays from the sun and cosmic rays from much more distant places as well.
Mm-hmm. Well, listen, all these asteroids that are out there, and you're saying there's one in 2029. How do we know this? Is somebody tracking them?
There are several programs, mostly financed by NASA, that are searching for asteroids, and particularly anything that might be dangerous to the Earth. So in Arizona, the University of Arizona, on a NASA contract, has major telescopes in Arizona that are searching for asteroids. NASA itself runs telescopes in Hawaii that are also searching for asteroids. And they find many of these close approaching ones per month. There is also the European Space Agency is running surveys. I think the Japanese are too, but the two American programs in Arizona and Hawaii are by far the most productive.
Okay. And what about you? Are you playing any role in tracking them?
We follow up new discoveries because we're a few hours behind.
What do you say? That's you and Pam, yeah?
Yes, the two of us. Yep.
Right, yeah.
We because we're in longitude, a few hours behind Arizona and Hawaii, we can be very useful in following up new discoveries, particularly fast-moving objects. I should also mention that Mount Palomar also finds, in California, finds some of these objects as well. And we have occasionally been quite useful in following up fast-moving ones that are close to Earth that would otherwise probably get lost if they weren't immediately tracked. We also,
sorry, carry on.
We also we try and extend the time they're observed for as long as possible, particularly objects in the south, so that their orbits can be most accurately calculated. We also try and find objects that are predicted to be approaching the Earth again, objects that were discovered many years ago, sometimes, that are approaching the Earth again. If they're in the southern sky, we try and find them.
So how would that work? Do they ring you up? Do they send you a text message, and then you rush out? What happens?
There's a website. The central clearinghouse is called the Minor Planet Center, and it's based in Cambridge, Massachusetts. It's part of the Smithsonian Astrophysical Observatory. And the Minor Planet Center has web pages where new discoveries are posted. So they have, for instance, what they call the NEO, the Near Earth Object Confirmation page. And on that, any asteroid that looks like it might be a near Earth object, and whose orbit might be a near Earth object, it's not known previously, goes onto that page. And then they rely on a whole network of amateur and professional astronomers around the world to follow up. So it's a fairly informal arrangement. They also post lists of objects that they want followed up as well. And that's where we would pick up these objects that are coming back that have been discovered many years before.
So how does it work? You know, you're sitting down to have dinner, and all of a sudden you check the website, and you realize, there's something for us to spot tonight, and then you rush out. Is that how it works?
That's pretty much it. Well, we get allocated time on Mount Trump's 1 meter telescope.
Right.
And we, in the afternoon before, we keep our lists, keep lists of objects that need to be followed up. So I prepare all the information for that, what we call ephemerides, that is lists of the position of the object, like every half hour through that night, something like that. But then during the night, we're also checking the NEO confirmation page to see if there's any new objects that have popped up. And so we quite frequently add objects in that have just been discovered a few hours before by these programs in Arizona and Hawaii.
Because I remember a couple of years back, I was in Wales, and I went to, it was either Knighton or Kington. I can never quite remember which is which. They're both close to each other. And I went, there's an observatory up there that does this NEO tracking. Have you heard of that? Have you heard of that guy?
I can't bring a place in Wales particularly to mind, but there are 2 or 3 amateurs in the UK who do asteroid tracking. The most notable one is Peter Birtwistle, who lives, I think, near Oxford. There's somebody in Cleethorpes, which I think is up the coast.
Lancashire, isn't it? Cleethorpes, or is it Yorkshire? Sorry, one of those up north. No, this guy had a little planetarium in there, and it was a wonderful spot, really wonderful spot, right up on the mountain. And right. He showed me all these programs, and it was quite fascinating. But is this your main astronomy interest these days? Asteroids? Yeah,
we also track comets. That if there are comets are generally well observed by most amateur astronomers, but occasionally you get, if comets are faint, then they're too faint for small telescopes. So we keep an eye on any comets that aren't being regularly observed by other observers. But asteroids are the main thing that we do, yes.
Alan, I meant to ask you this at the start, because people who are watching or listening probably don't know what a well-known chap you are amongst the astronomy community. And like I said, you and Pam were on that stamp. How did that happen, by the way?
Not really sure.
It's unusual. Somebody calls you up. Hello, Alan. Yeah, would you like to be on a stamp? Oh, yeah, all right.
the first we heard was when we got called up and asked for basically biographical material. And I said, oh, yes, that's fine, but what do you want it for? Oh, we're putting you on the stamp. That was it was a nice honor, but I think that there were other people who really should have been considered before us in New Zealand astronomy.
You never called me, Alan, I can tell you that much. Well, that's very good. That's very nice of you to say. Very self-effacing of you to say, but I'm sure that you're on there for a very good reason. Yeah, what is that reason?
Well, the rationale was that we had been observers of one sort or another for, over 40 years. We started the program, the Comet and Asteroid Tracking Program at the Carter Observatory back in 1973. It really got underway. And then we came down to Mount John and continued it. So we've been observing southern comets and asteroids and other things as well for Canterbury University for their programs for getting on for 50 years. Wow.
50 years. You must have started when you were 5 years old, Alan, is that right?
Oh, I started back, that's the sort of professional astronomy, if you can call it that. I started amateur observing at age 15 back in 1959. I started variable star observing, that is making estimates of the changing brightness of certain kinds of stars that vary in brightness. I began that,
Wow. What was it that got you into astronomy?
I don't know. I guess one just is wired up in a particular way. We lived in the country when I was quite young. My dad was in the railways, and we lived in a railway settlement on a branch line long since closed out of Gisborne. And we were walking home from visiting friends one night, and I saw a star fall. And I was very fascinated by this. My dad was very well read. He explained that it was a rock falling from space. I don't know how much I understood at the time, but you sort of stored this away. And then when we moved to Wellington, although he took me to the Carter Observatory, which had public sessions, and I saw the moon and so on through a telescope. And so that really got me interested.
How different from my upbringing? You know, when I was walking home with my dad in Merthyr Tydfil, I remember seeing a drunk fall. And what's he doing? To be born in New Zealand. That's the way.
The country area. Yeah, but then what really got me into properly using telescopes was a little book in the Hutt Intermediate School Library, which had a little star atlas in it and had drawings of what planets and things looked like in a small telescope. So I got a job after school and saved up money and built a 6-inch telescope with a lot of help from my dad.
As one does. And
then I wrote to the Carter Observatory saying, what can I do with this telescope? And they said, variable star observing, right to Albert Jones, actually it was, who was a
Albert Jones? Q, wow. Yeah.
And Albert tutored me long distance. He was living in Timaru then. So I learned how to do variable star observing. That got me in touch with Frank Bateson, who ran the variable star section. He was based in Rarotonga then, running an island trading company. And then when he came back to New Zealand to run the site testing program for the University of Pennsylvania, when they were looking for a place to put what became Mount John Observatory, I got a holiday job. By this stage, I was in the 6th form. I'm not sure what years these are. I think these are about year 12 or year 11.
Hey, Alan, you're only 16. Is this going to go on for a long time?
No, by this stage, I'm getting up.
Oh my 18. God.
Yeah. You might have to edit this out of it. Yeah. And so then I worked on the variable star. I worked on the site testing program for Mount John in school.
And the rest is history. Well, thank you, Alan. Now tell me, what is your favorite astronomy song?
don't know any astronomy songs, really.
I want everybody to know that before this broadcast, I contacted Alan and said, "Tell me what your favorite astronomy song is." And now, at the end, you don't know.
Well,
Starman,
yeah,
that's Starman, Fly Me to the Moon.
Yeah, there's those sort of songs. Way back, there was a musical called High Society, and in that,
Would you like to swing on a star? Is that it?
No, Bing Crosby and
Frank Sinatra.
Frank Sinatra sing a song where with one of the little sides is, "Have you heard It's in the Stars? Next July we collide with Mars."
Well, did you ever?
What a swell party this
A swell party. A swell party it is. And with that, you're going to hear an even more wonderful song coming from yours truly. Alan, it's been a pleasure to talk to you, really has. And we definitely want to have you back again, talk about something else. We could talk about asteroids again, but the audience might get a bit restless. So we'll get you in to talk about something soon. And hope it clears up down there in Tekapo. And yeah, here we go with my favorite singer for sure. Bye, everyone. Take me to Callisto so I can see the stars. I want to view the Milky Way from a terraform base on Mars. From a terraform base on Mars. From a terraform base on Mars.